Hello students, welcome to online maths classroom. Today we are going to start with logarithmic differentiation. We will do the concept and exercise 5.5 question number 1 to 5. So let us start with it. Logarithmic functions. Let us recapitulate what were logarithmic functions. As we have done in earlier class, that if b raised to power y is equal to x, this is the exponential form. Okay, b raised to power y is equal to x, then this y which is in power, this is equal to log to the base b of x. Okay, or otherwise we can say that log to the base b of x is equal to y. Okay, so let us take some simple examples to understand the exponential form and its conversion from exponential to logarithmic form. Okay, as you know, if 5 square is equal to 25, then according to this definition, it will follow that log to the base 5 of 25 is equal to 2. See. Similarly, 3 raised to power 4 is equal to 81. It will follow log to the base 3 of 81 is equal to 4. Okay. 10 raised to power 0 is equal to 1. It will follow log to the base 10. Okay. See, whose power is there? B. Okay. Log to the base 10 of 1 is equal to 0. Okay. So this is how we convert exponential form to logarithmic form. Now let us understand what is the relationship between exponential and logarithmic function. Okay, as exponential function is what will be the answer if a number is raised to a certain power. So see, 2 raised to power cube. Okay, so input is your 3. Okay, so 2 raised to power cube, what will be the output? It will be 8. Okay, now logarithmic function, if say I want to know that 2 cube is equal to say 8, logarithmic function will answer this question. Okay, that at what power a number must be raised to get a particular number. Okay, so that if I want that 2 raised to power n is equal to 8, then what was it number? So I will get it as that n value should be equal to 3. Okay, so like 2 raised to power what is equal to 8 implies log to the base of 2 of 8 is equal to 3. Okay, as we did in the earlier example also. See from here, log to the base 2 of 16 will be 4. Why? Because 2 raised to power 4 is equal to 16. Similarly, log to the base 3 of 27 is equal to 3. Why? Because 3 raised to power 3 is 27. Similarly, log 10 of 1000 is equal to 3. Okay, log 10 of 1 is 0. Okay, why? Because 10 raised to power 0 is 1. And log 10 of 10 is 1. Why? Because 10 raised to power 1 is equal to 10. Now, exponential and logarithmic functions. Okay, when we plot the graph, okay, see, we plotted the graph of say polynomial function. We have learned about polynomial, rational, trigonometric functions. Okay, now in this section we will be learning about a new type of function that are called as exponential and logarithmic functions. Okay, now let us understand these functions with the help of some examples. Say this is the graph, this figure is there in which we have plotted few graphs. Okay, so you're familiar with it, y is equal to x graph. Okay, when we plot say graph of y is equal to x cube, it is like this. Y is equal to x cube, it is like this. This is y equal to x square, y equal to x4, y is equal to 10 raised to power x. So you see, as the power of x is increasing, the graph is getting steeper. Steeper means it is getting more straight. Okay, so we come to the discussion that there is there is there is the power change, means the degree of the polynomial function, higher the degree, greater is the growth. Say this growth, this growth is a bit slower, this one is fast. X cube is fast as compared to x square, like x4 is fast as compared to both x cube and x square. Okay, so the greater the degree of the polynomial, the greater is the growth. Okay, so is there a function whose growth is more faster than this, any of these polynomial function? Okay, so you will get an example that yes, there is a function like y is equal to 10 raised to power x, which is having more faster rate of growth as compared to such kind of polynomial functions. Okay, now with the help of this 10 raised to power x is a sort of your exponential function. So let us understand what are your exponential function. The exponential function with positive base b greater than 1 is a function y is equal to fx, which is equal to b raised to power x. As you know, when we talk about 10 raised to power x, then b was having the value as 10. It can be have some any real value like 2, 3, 4, something like this, but it should be greater than 1. Okay, so a function defined with positive base b greater than 1, y is equal to b raised to power x. Okay, so let us see what is from the graph. Let us understand what were the features. First of all thing is that domain of the exponential function is the set of all real numbers. Okay, set of all real numbers. You can put the real values. Range of the exponential function, this is also going to be your real numbers. You keep on putting like 10 raised to power 1, 10 raised to power 2, 10 raised to power 3. You know you are putting real values and you will get your real numbers also. The point 0, 1 is always on the graph of the exponential function. Okay, you saw that the graph of 10 raised to power x, it was having point 0, 1. Okay, so you will always find that the point 0, 1 is always on the graph of exponential function. Now one reason is behind that, because anything raised to power 0 is 1. So b raised to power 0 is also 1. That's why 0, 1 will always be on the graph of exponential function. And number 4 is that exponential function is ever increasing. As we move from left to right, the graph rises above, as you have seen the graph of 10 raised to power x. For very large negative values of x, the exponential function is very close to 0. Okay, you know, as the function is having say 10 raised to power say minus 19. So it will be 1 upon 10 raised to power 19 and the value will be getting more closer to 0. Okay, for very large negative values of x, the exponential function is close to 0, or in the second quadrant the graph approaches x-axis but never meets it. Okay, it will be parallel but never meeting it. So exponential function with base 10 is called as common exponential function. Okay, like, and your this appendix of previous class, it was there that sum of the series 1 plus 1 upon 1 factorial plus 1 upon 2 factorial plus so on. So this is a number between 2 and 3 and is denoted by e, and this e as the base we obtain an extremely important exponential number y is equal to e raised to power x. See, it was y raised to power y equal to 10 raised to power x. Now it is y equal to e raised to power x, and this one is called the natural exponential function. This was your common exponential function and this one is your natural exponential function. Okay, now let's go to how it is related to logarithmic function. Now let b is greater than 1 is a real number. Then we say logarithmic of a to the base b is x if b raised to power x equal to a, as we did in the definition of logarithmic functions. Okay, that is, you know that log to the base b is having domain of positive real numbers and the result is your all real numbers. So if b raised to power y is x, then your log to the base b of x is equal to y. Okay, now see the graph of your logarithmic functions. Now you see that if we take about, this is all about bases. So log to the base 2 of x, it is like this. Log to the base e of x, it is like this. Log to the base 10 of x is equal to like this. Okay. Okay. Now let us see the properties of log function. The range of log function is the set of all real numbers and the domain is R positive. Okay. R positive. Okay. The point, as in case of exponential function, 0.01 was always there on the graph. Here for log function, the point 10 will always be on the graph. This was for exponential, 1 was on the graph. So here 10 will be on the graph. The log function is again ever increasing function as we move from left to right. Okay, from left to right. For x very near to 0, the value of log x can be made lesser than any given real number. Okay, very close to 0, the value can be made lesser. In other words, in the fourth quadrant, the graph approaches y-axis. Okay, so as we go down, it approaches y-axis but never meets it. Okay, and the plot of y is equal to e raised to power x, and the y is equal to log to the base e of x. You can see, and if we look at both these graphs, and this is the line y equal to x, you will find that they both are mirror image of each other. About this line y is equal to x. Okay, so these are both mirror image of each other. Now let us see how the law of exponents are connected with law of logs. Okay, so in your junior classes you have studied laws of exponents. Okay, so let us see how they are related with law of logs. So you know, x raised to power m into x raised to power n is equal to x raised to power m plus n. If bases are same, powers are added. So this is the law of exponents. Now how is the law of logs? Log a into b. Okay, log of a into b is equal to log a plus log b. Okay, for division, x raised to power m upon x raised to power n is equal to x raised to power m minus n. This was law of exponent. Now for your logs, log of a upon b is log of a minus log of b. Numerator minus denominator. Okay, x raised to power m whole raised to power n. That is, it can be written as x raised to power mn, means these powers are multiplied. Now, this is a very important property of log, that is log a raised to power n is equal to n times log a. The 0 property was there, anything raised to power 0 is 1. So, here it is applied as log of 1 is equal to 0. Inverse property of exponent was like x raised to power minus 1 can be written as 1 upon x. Now log x raised to power minus 1 can be written as log 1 upon x, and using this property, say it will be written as log 1 minus log x. Now log 1 is your 0, so it will be minus log x. Okay, so now let us see the properties with the help of examples, the very important properties that we will be using. That this again same property, log of m into n is log m plus your log m upon n is equal to log m minus log n. So see here, this base is not important, base is there, it will be primarily taken. Okay, but how will I write? Log 4 minus log 5. Okay, base will be retained. Log, say to the base b, m raised to power p can be written as p log to the base b of m, like this. Okay, so log 2 8 raised to power x can be written as x log to the base 2 of 8. Similarly, equality says that if log to the base b of m is equal to log to the base b of n, that means m is equal to n. Similarly, for this question, you can find that 3x minus 4 is equal to 5x plus 2. Also, you are familiar that derivative of e raised to power x is e raised to power x, and the derivative of log x is 1 upon x. ddx of log x is 1 upon x. Okay. So let us utilize all the concepts learned here to solve your exercise 5.5 question number 1 to question number